Now I'm going to solve one problem. Okay. The problem is a 6.6 kilovolt 3-phase star connected synchronous motor. Okay, star connected synchronous motor takes a line current of 50 ampere. The effective resistance and synchronous reactance per phase or respectively 1.5 ohms and 8 ohm. Okay, calculate first subdivision. The power developed, the power supplied to the motor to the induced EMF for a power factor of 0.8 lakh and lead. Okay, and lead. Now we'll solve the problem. Solution. First step is solution. So in solution, what are the given data are available as per your problem? You see here a 6.6 kilovolt 3-phase star connected. Okay, so the machine is star connected. It is mentioned in your problem. It is star connected. Okay, and the voltage value which is mentioned here, it is 6.6 kilovolt. That is line voltage. V line equal to 6.6 kilovolt. Okay, then line current IL equal to 50 ampere. IL equal to 50 ampere. Now, since the machine is star connected, you know the formula for star connected. In star connected, the line voltage is equal to √3 into V phase, but line current is equal to phase current. Line current equal to phase current. So now we have to calculate the phase voltage. Phase voltage. V phase equal to V line divided by √3. Okay, divided by √3. Now substitute the value. V line is how much? 6.6 kilovolt. Substitute 6.6 into 10 power 3 divided by √3. What is the answer? Anyone? Please give me the solution. Anyone? Please give me the answer, ma. Girls, what's the answer? 6.6 into 10 power 3 divided by √3. How much?
So 3.81 into 10 power 3.
3.81 kilo volt, kilovolt. Okay, and the line current. Okay, line current we have to calculate. So what is my line current? In star connected, we know that the line current is equal to phase current. Okay, since this is the my armature. Okay, here only the windings are there. Windings are there. So in armature only you are going to give three phase AC supply. The armature is nothing but it is a stator. Okay, it is a stator, that is nothing but armature winding. So the current flowing in this wires, three wires, it will be line current. Okay, so this line current we have to, because the line current data it is already available in your question, so we have to convert into phase, because whatever the values which we are going to calculate, everything should be a phase. Okay, line voltage, phase voltage, EMF induced per phase, everything should be in phase. Okay, we have to calculate it. So based upon that concept, we are going to measure the phase current. Okay, since the machine is star connected, the line current equal to phase current. So where this phase current will be entering, it will be in armature. So in armature only we have to represent IA phase. Okay, so IL equal to I phase, that is nothing but IA armature current phase. So we can represent I phase or IA phase. So what is the value? It will be 50 ampere. It is 50 ampere. Okay, then one more data which is available here, you see in your question, the effective resistance and synchronous reactance. Okay, effective resistance and synchronous reactance. So effective resistance means RA equal to 1.5 ohms, 1.5 ohms. And synchronous reactance, see everything will be per phase. Synchronous reactance X S equal to 8 ohms. So the combination of resistance and reactance, it is nothing but impedance. Z, yes, impedance is equal to RA plus J X S, J X S. Now substitute the parameter. So how much your RA? It is 1.5 plus J8. So now it is in rectangular form. Okay, this format it will be rectangular. Now can we convert it into polar? Please convert rectangular to polar. Convert rectangular to polar form. Anyone give me the answer? What is the answer? 1.5 plus J8.
So 8.139 angle 79.38.
8.139 angle 79.38. Okay, 79.38 degrees. The unit of impedance will be ohms. Okay, now we'll get into the problem. Now what you are going to calculate? Calculate power supplied to the motor. Okay, that is my first method. Calculate power supplied to the motor. Okay, now we'll see one by one. First one, power supplied to the motor. So the power supplied, which is nothing but input power. Power supplied means which is the input power. Okay, P in, this one only you are going to calculate. P in equal to root 3 VL IL cos phi. Now substitute all the parameters inside. Root 3 into VL how much? VL line voltage 6.6 into 10 power 3. 6.6 into 10 power 3 into IL. IL will be, it is 50 into power factor. You see your question, power factor is they are already given, it is 0.8. Okay, how much? What is the answer? Anyone? Power factor is already given in your question itself, it is 0.8. Please give me the answer. Final answer. P in how much? Anyone? Give me the solution. P in. Sartak Das.
So 45726.41.
45761.41.
457.261 kilowatt. The unit of power is watt. Okay, kilowatt. 457.261 kilowatt. Okay, that is my first subdivision. Now, next subdivision, second subdivision, we are calculating the induced EMF for a power factor of 0.8 lagging and leading. Okay, 0.8 power factor lagging. First we will calculate power factor for lagging.
He wants to submit a Lada recording. I can give it to you only.
HV.
Guide kite kutta so we can use sir.
Okay, cos phi equal to 0.8. Okay, now we are going to measure induced EMF in lagging. So what is the formula for lagging? Can anyone tell me what is the formula for lagging? Yesterday class explained it. What is the formula for lagging? Anyone? EB, induced EMF, EB.
Root of V phase square plus ER phase square minus 2V phase ER phase cos theta plus for lagging is theta minus 5.
Yeah, lagging means theta minus phi. V phase square plus ER phase square minus 2 V phase ER cos theta. What symbol? Since it is lagging, okay, we have to put minus 5. Okay, now substitute all the parameters. So how to substitute it? How to substitute V phase? V phase we already know. It is 3.810 into 10 power 3. 3.810 into 10 power 3 whole square plus. How to calculate ER? Can anyone tell me how to calculate ER? What is the formula to calculate ER?
IAZS.
Yeah, ER equal to IA into ZS. Now IA, it is 50, right? 50 into ZS, it is 8.139 because we are just multiplying only the magnitude. Okay, 8.139. Okay, because current is not having any angle. Okay, so we have to consider this is 8.139 will be magnitude. It will be magnitude, and 79.38 it is a degree. Okay, so 8.139 I am multiplying it. So how much more?
406.95.
406.95 volt. Okay, this is my ER. Okay, now substitute here. ER 406.95 whole square minus 2 into 3.810 into 10 power 3 into ER 406.95 into cos theta. Theta how much? Can anyone?
79.38.
Theta value it is 79.38. Yeah, it is there in impedance. Okay, this 79.38 which is nothing but theta. Good, 79.38. Okay, the theta value we have to measure from impedance. Minus 5 how much? Cos phi equal to 0.8. So therefore 5 how much?
36.86.
36.86. Okay, and put a common bracket. Now give the answer. Girls, only boys are giving the answers. What about girls? Huh? Grishma, Grishma, Sahana, give me the answer.
It is 3.520 into 10 power 3.
Good. 3.520 into 10 power 3. That is kilovolt. This is my EB phase. This is my EB phase. Okay. Then, in the second subdivision itself, we have to measure induced EMF EB cos phi equal to 0.8 for leading. For leading. So, what is the formula? Because already you know EB phase. So, in this existing formula, what I have to make a necessary changes? What I have to do? Yeah, since it will be leading. So, in leading, which symbol will be varying?
Cos will become
Cos
plus.
of theta minus phi.
Theta plus 5.
Yeah, this is theta phi. Only there will be a changes will be taken place only in theta minus phi. You have to change it to theta plus phi. So write V phase square minus 2 into V phase ER cos of theta. So here I have to put plus. Okay, I have to put plus 5. Now substitute all the parameter. 3.810 10 power 3 whole square plus 406.95 whole square minus 2 into 3.810 into 10 power 3 into 406.95 into cos 79.38 plus 36.86. Now can you give me the answer? EB phase how much?
4.006 kilowatt.
4.006 kilovolt. Okay, therefore in lagging leading EB phase equal to 4.006 kilovolt. Okay, so now compare this EB value. Okay, you see, you please check. Okay, generally in lagging and leading, we are checking the power factors with respect to the phase voltage. With respect to the phase voltage. So in leading, what happened? In lagging also you can see the condition here. Okay, here I can write, because we are getting EB phase is equal to 3.520. So therefore I can compare this EB phase value. Okay, since it is lagging, okay, it is lagging it because the condition we are measuring for lagging. So EB phase value which is lesser than V phase. You see here, EB phase we got 3.520, but V phase we got 3.810. So the condition is EB phase will be lesser than V phase. Okay, in leading also you have to compare this EB phase with your V phase. So EB phase will be greater than V phase. So from that, what you are understanding, because of the EB phase is less than V phase, the what is that, the oscillations which has been taken place in the machine, it is nothing but under excitation or over excitation or critical excitation. Can anyone tell me? It will be which condition? This one, EB is less than V, which is comes under which condition, ma? It is over excitation or under excitation?
Under exit.
Yeah, this is under excitation. Under excitation. Okay, and this condition for over excitation. To limit this over excitation terms, we are introducing the capacitors or damped winding arrangements in the existing structure of our synchronous machine. Okay, of our synchronous machine. Any doubts in this problem? Any doubts, students? If you have doubts, please ask me. The phi value you can take it from power factor, but the theta you have to measure it from impedance. Okay, that is only one difference. Any doubts? Now I will explain the difference between the synchronous motor and induction motor difference. This is one 5-mark question. Difference between synchronous motor. I can write full name. Synchronous motor and induction motor. Induction motor. First, here this line will be parameter. First one, construction. First point is construction. So the synchronous motor construction is complicated. It is somewhat complicated because there are two winding structures are there. One is field, another one is armature. Here the construction is simple. Induction motor. Second point, starting. Parameter is starting. Synchronous motor, it is not self-starting. Not self-starting. But induction motor, which is self-starting. Third, here DC source, that is, you are giving DC excitation, right? Here it is available because we are giving DC source to field winding, but here it is not applicable. It is not applicable. Fourth, speed control. Fourth point, speed control. In synchronous motor, it is not possible. It's not possible means because the synchronous motor will be running at constant speed at 1500 rpm. Here, induction motor, it is possible because it is running at two speeds. One is synchronous speed, another one is rotor speed. Fifth, cost wise, cost. It is very high. It is very high, which is cheap. Sixth point, here the machine will be running at speed. The machine is running at constant speed. It is variable. Seventh point, maintenance. It is frequent maintenance needed. Frequent maintenance required. Okay, here it is free. Okay, no maintenance is required for this. Okay, and eighth point, power factor improvement. In synchronous motor, we can able to improve the power factor by synchronous condenser. But here it's not required because synchronous condenser will be absent. Understand? And ninth point, excitation. So by changing excitation, the motor power factor can be changed from lagging to leading. That is, the power factor changed from lagging to leading. It is possible in excitation. Okay, where we are giving excitation in field winding, in synchronous motor. But here it is not, excitation not available, so you can't shift the power factor from lagging to leading. It's not possible. 10th point, load. When load increases, load angle alpha is also be increases, but we have to keep speed constant. Okay, but in induction motor, if load increases, speed decreases. Okay, so these are the, it's one of the disadvantage in induction motor. So there are 10 points are there, the difference between the comparison of induction motor and synchronous motor. The first point will be in construction. In synchronous motor it is complicated but it is simple. In starting, synchronous motor it's not self-starting, but induction motor it's a self-starting motor. And DC source, yeah, in synchronous motor a DC source will be available for field winding, but there in induction motor not required, no field, no DC source. Parameter 4, speed control. Speed control is not possible in synchronous motor, and induction motor it is possible. Cost wise it is very high, synchronous motor it is very high, induction motor it is very cheap. Speed, synchronous motor it is very constant, but induction motor is variable. Maintenance, it is frequent maintenance required, but here it is free. Power factor improvement, how to improve the power factor in synchronous motor? By introducing the synchronous condenser. Okay, that is nothing but synchronous capacitor. Okay, in synchronous motor, but in induction motor synchronous capacitor or synchronous condenser is not required. And ninth point, while giving the excitation to the field winding which is connected in the rotor side, so we can change the power factor of the motor from lagging to leading. But in induction motor it can always be operate at lagging power factor, and lagging power factor only we can operate in induction motor. Okay, and the load, when the load is increases in synchronous motor, what happens to my alpha? It is increases, so therefore the synchronous speed will be constant. Here in induction motor the load increases, the speed will be decreases. Okay, any doubts?